Hi everyone. So let's resume now, and we're going to do the lecture on basic deep learning and PyTorch. So the first comments to make are about AI in general, and then machine learning. So a lot of times in AI, what we can do is we can look at basically what are toy worlds. So historically, there was like this blocks world, or there were games of like Connect Four or Tic Tac Toe, and then that came up that in game playing that became something like maybe checkers, then was attacked, and then chess, and then finally Go actually got attacked. So Go is an interesting case that we'll talk about later. But anyways, these are kind of simple like little worlds where you can kind of grind out all the possibilities and evaluate results based on kind of a finite set of rules, like the rules of the game. This there was kind of some initial work there. And then in many domains, we could code knowledge and actions in logics. And actually, what those do is they compress the state space into a logical description. So a lot of times a logical description will cover either many states, or it will cover an infinite number of states so that are compatible with that logic expression. So when you get up to things like planning or rule-based systems, a lot of times that was the underlying kind of architecture of the AI system. So this went along for a long time, but machine learning is an old field. I mean, there was like Samuel's checker player. There's lots of lots of these problems were attacked early, but more and more, what happened is that we started looking at problems that were very difficult to actually treat this way, where we just kind of like take in all the dimensions and kind of grind out all the possibilities. So this kind of, so the idea here then is that, well, what if we basically use a wealth of data to induce a performance element that actually, so it learns from the data, and then it can do the task. So things like object recognition, for instance. So this is machine learning. So this is kind of what kicks off machine learning. And then in machine learning, the two primary modes of machine learning that we're going to start with in this course are supervised and unsupervised. There's lots of other distinctions like semi-supervised. You'll see people talk about that, but which is a mix. And like I would say that the four really kind of fundamental paradigms of machine learning are supervised machine learning, where you're given a whole set of input-output pairs. Example. So this is the input. This is what the output should be, and then what we do is we go through. We're given a test set. We're given a training set. And we're also given a validation set. We'll talk more about validation sets later. But the idea is that we're given the training set. We build the performance element. We induce a performance element based on the training set, and then we evaluate it over the test set. Okay, and then we can we can calculate some type of accuracy. Unsupervised is interesting because unsupervised, we're just given unlabeled data. So we're just given a whole bunch of data, and then we induce something that can capture that data, or capture the patterns, or capture the distribution of that data from just seeing a whole bunch of unlabeled examples. So that's your unsupervised learning. And we'll see that the basic training for GPTs is unsupervised. Okay, and then when we get into SFT, that will be supervised. Okay. And then when we get into the RLHF and RLVR, those are, of course, reinforcement learning. Reinforcement learning we'll cover later. So that's kind of a different machine learning paradigm, where you don't get the rewards immediately. You get the rewards kind of displaced after a whole bunch of actions. And then you have to go and you have to assign, well, it's kind of like do good things like, study, get good sleep, et cetera, do all these things in your life, and then you'll get these rewards at the end. But you have to kind of trace back those rewards to those kind of fundamental those actions, and it's kind of removed in time. So it's much more complicated. So with reinforcement learning, explanation-based learning is interesting. It doesn't get talked about much these days, but explanation-based learning or one-time learning is something where you're using knowledge in your learning. So the classic example of that is that when the child touches a hot stove, they only do it once. They never do it again. So they learn from one event. One event changes their performance element. So it's not like they need to have a whole bunch of cases of that. So they form an explanation in their mind about why something happened, and then based on that, they are able to kind of like induce knowledge that they use later on in the performance element. Okay, so we'll talk a little bit about that later in the course. It's an interesting area. I think it's been overlooked. So. Right. Okay. So what we're going to focus on today in today's lecture is a subset of this of machine learning, which is focused on deep neural networks. So a lot of the classical learning algorithms are, I mean, here's a list of some of them, like linear regression, support vector machines, naive Bayes, logistical regression, okay, k nearest neighbors, decision trees, random forest, gradient boosting. There's a bunch of different sub techniques there as well. K-means clustering, DB-scan, principal component analysis, collaborative filtering. Okay, so these are all really kind of. I mean, a lot of times, I mean, for a lot of things in the real world, like if you need to like the controller inside of an appliance or something is going to be based on. It's going to be based on machine learning. It'll be based on something like one of these, or something that's kind of a very fundamental little step in a process, especially a process that's very mission critical and that you can't take chances with. A lot of times, these will rely on these kind of classic engineering methods of machine learning. So things that like kind of like the control system for an aircraft or something like that. I mean, that's going to be you don't typically you don't have deep neural networks doing that. Because deep neural networks are a little more organic, they're a little bit more grown, and you can't really kind of have that many assurances over them. But the classical algorithms, which we're about to just bypass, they're very heavily dependent on representation. So the mapping of what are the aspects of the problem to a set of features that then become the relevant features you're doing maybe a data fit over. So that would be in something like logistic regression. Like you might have like, oh, these are all like, well, let's try to detect whether the patient has diabetes or what's the likelihood of them having diabetes. And we have all these different features that we've engineered, like asking, well, you know, how old are you? That's one feature. What's your BMI? These kind of things. And then maybe some blood tests come into that as well. So these are all features that we've kind of engineered that should be relevant to the problem. And then we do a linear combination and then send those through a sigmoid or logistic function. Okay, and then that basically that's kind of that is kind of a process by which we build the system or we engineer the system. Now, the thing about that though is that a lot of the work then goes into getting the right representational features in a particular problem domain. So that becomes very, very kind of problem domain specific to get those. What happens in deep learning, so there's a lot of effort in that. Now, what happens in deep learning is, so this is an example here of deep learning where we're potentially recognize this as our grandmother. Okay, so, or our mother, maybe, I don't know. Anyways, she's a bit young to be my grandmother, maybe your grandmother, or maybe like a little baby's grandmother. But she looks fairly young. But anyways, let's just say that she's a grandmother. So up here we have a node representing grandmother. That's the grandmother. And maybe this one over here is for like the grandfather. This one over here is for like a car or something, right? So these can be as many different things. These nodes here represent what we're trying to recognize. So in this case, we're trying to recognize our grandmother or the grandmother. That's this node here. This node lights up and this one gets the majority. This one gets the strongest signal. And that would mean that this neural network had decided that the image given to it was the grandmother, okay? If this lights up instead, it means that it was the grandfather. If this lights up, it means it's the Buick, the car, or whatever it was. Okay, and there, of course, might be many more of these because, you know, who's going to have just object recognition overall, just that small set. But anyways, I hope you get the idea. So, what's really kind of strong about deep neural networks is that all they do is take in the very low level pixel features. Those are the features. So there's not much engineering of representation here. It's just let's take the pixels, and we feed those into the first layer, layer one of this neural network, and then so the first step of the program is to take the raw image here, to pass it in and then calculate the next level. Okay, so this is, you can see this is kind of a process of computation where we're kind of doing what's called a computational graph, and we're moving the signal through this network. Now, in the very beginning, these are all just random weights. They're all just random weights. But what we do is we use an algorithm called backpropagation to take whatever error we get up here. So let's say, for instance, that we put in the grandmother, and then we pass everything through, and we get out, oh, it thinks it's a Buick, it thinks it's a car. Okay, that's wrong. So we're going to pass back a lot of error, and then it says maybe it's got a small signal here saying that it might be the grandmother. But what we do is we basically say, okay, that's you got to go. You got to like move in a completely different direction to kind of like boost that signal, right? So what backpropagation doing is it's calculating what's called the gradient of the weight space. So the weight space here, I mean, how many weights are there here? Well, there's a weight for each of these links, so we can just calculate how many weights there are in this network. So maybe actually when I give this, I'll ask people, okay, well, how many weights are in this network? All right, well, if you just do it kind of in a simple way, you got the full, yeah, you can count them up, right? You can count up how many weights there are in this network. So that's a giant, typically it's a theta. It's a giant theta, right? That's all the weights. And then when we get grandmother put in here, and then the output is something or other, it's not perfect though. It's not saying 100% grandmother and then everything else is zeros. It's not doing that quite yet. It will get toward that. But when we start out, it's just kind of almost randomized. So what we do then is we calculate, well, what's the gradient? What is the, and I don't know if there's, it's going to be 3 times 3. It's going to be, let's say there's 9 plus 9 plus 9. Let's say there's 27 parameters. I might be wrong about that. 27 parameters in theta. Then that determines a 27-dimensional vector. And what the gradient tells us of this whole system is it tells us, okay, what direction should that vector go in to minimize the error? Okay, so that's the key thing. So, well, whatever it is, we make a slight adjustment then to the weights, and then maybe we bring in another image of, say, the grandfather or the Buick, the car, and then we just go through our whole training set. And then if we go through the whole training set once, that's one epoch. And we do 2 epochs, 3 epochs, and we have this learning rate, and we start converging towards something that is getting better and better. Okay. Then we have, of course, the test set, and we evaluate against the test set. But the point here is that what happens inside the system is we're not doing any like engineering of features. It's actually learning more abstract features as a byproduct of just this training method or this gradient descent. So this is called stochastic gradient descent. This is like the basis of all deep neural networks, and including transformer networks. This is how they train. Okay, so that's an intuition I hope that you get from that. All right, so let's move on here a little bit. So okay, so why deep neural networks now? What's the big deal here? Okay, so well, with deep neural networks, I already talked about this representation learning. So data sets can be cheaply represented with low-level features. Learning automatically abstracts to higher level features the deeper you go into the network or into the computational graph. Okay, so you can view each layer as a deep neural as performing a step in a computation of a computational graph. All right. Okay, another reason why deep neural networks have really kind of become so strong is because we have so much data. Okay, so it's enormous quantities of data, both supervised and unsupervised. And in this case, we're doing a supervised example with the grandmother and grandfather and the Buick, the car. Another reason why this works much better now is because we just have so much more capacity. There's hardware, the infrastructure. It's just a lot more convenient to kind of run these kind of things. And then we have some really good software now that really helps with this, and that's what you're going to get experience with PyTorch. Okay. So let's talk a little bit deeper. I'll do this very quickly because it's kind of a bit of a mystery. So a lot of a lot of the big researchers in deep learning, they say, well, we don't really, who knows why we can't give an explanation for why this particular weight is set a certain way. It's kind of a distributed computation. It's just part of a convergence of all of the parameters, but they just kind of wind up somewhere, and then it's kind of like, okay, well, yeah, It's just like there. Thank you very much for. We've essentially grown this thing. We've grown those links just by doing the training, but we can't really explain each individual link, each individual weight. It's not really kind of accessible to explanation. So we just have to kind of well, but it does well, and then we do it on the test set, and it performs well. So we say that's good. Okay, but there can be things there can be issues there. So sometimes there's a lot. We'll talk about this later. Like for instance, there's this concept of a lottery ticket. So sometimes we get a genius network. We just are very lucky that it's because of the initial setup of the weights, we find a really good solution. Sometimes we don't find a very good solution. Sometimes there are problems in the solution. So it's all kind of like just like if you're a gardener and you plant a tomato seed. Sometimes you get really a nice tomato, nice bushy tomato thing out of it. Sometimes God only knows why, it doesn't work so well. Okay, so sometimes it goes that way with training these things. Right. Okay. So let's talk about some deeper motivations for deep learning. So in the traditional kind of classical representations, we have what's called the curse of dimensionality. So therefore, the more things you add to a problem, therefore the more dimensions to the problem, you're exploding the possible state space or the space of configurations of the problem exponentially. Right? So that's what's called the curse of dimensionality. That as you try to scale to bigger problems, you just get exponential number of potential states. Okay. Then another problem is that we have what's called this kind of local consistency or smoothness regularization. So a lot of times machine learning doesn't have anything more to go by other than to say that, well, if these are the inputs and that this is the result, then if I slightly perturb the inputs, I'll get roughly the same result. So there's this kind of smoothness kind of assumption that we apply over the whole domain. And this a lot of times works, but a lot of times it doesn't for various reasons. Sometimes there are very intricate, small little things that need to kind of be accounted for. And moreover, like I think the classic example to kind of illustrate this is, what if you were learning a checkerboard? So that is, you take the XY position and you determine is it black or white? Okay. Without anything other than the smoothness or localization kind of constraint, what you have to do then is you have to collect you have to gather pretty much data samples from everywhere in that whole space. But if you can recognize or you can see that it's a checkerboard and you get kind of a higher level kind of explanation for it, then maybe you can classify in a better way. So sometimes deep learning can kind of arrive at that kind of generalization. And then there's this kind of notion of manifold learning, which I think is the good way to kind of illustrate that is if I say the following. I say, well, tell me about or give me a trajectory of the trip you took to North America last year. Okay. Well, the trip you took, there are four measurements associated with each place you visit or your whole trajectory. There's the X and the Y. Let's just do this relative to the Earth's core. There's the X, the Y, and the Z, okay? But if you notice, you were always kind of on the surface of the globe, right? So like, okay, in the spatial dimensions, you can maybe just kind of like approximate that with like a two-dimensional map, right? And just take it as an assumption that other dimension is just, they're always at sea level, okay? So you can describe it in fewer parameters, all right? So, and then, if you talk about like fractional dimensions and stuff like that, you can even go down even further. You can compress it even further into maybe some kind of 1.6 dimension. So you're following points along this kind of warped manifold that represents the problem. And the point is that deep learning, in some sense, is getting access to that kind of automatically. It's kind of automatically getting access to that. And this is very, very difficult for classical algorithms to countenance. Okay. So these are some intuitions about why this works. Okay, so let's go back and talk a little bit about the history here. Okay, let's see if I can move that. Oh wow, ooh, that was nice. So this is integrated well into this Loom. So a lot of this work started out with the perceptron. Okay, now the perceptron is interesting because it's kind of logistic. We'll see what the perceptron is about here. So essentially, this is an old picture of it from Frank Rosenblatt at Cornell was the main kind of advocate of this way back in the 50s and 60s. The idea here was if you look right here, you could like write here like the digit 7. Okay, I write the digit 7. And then you tune this whole thing so that it recognizes a 7. So in this case here, wow, that really looks like a 7. So it kind of really goes, it's like a Geiger counter. It kind of like really goes off. But if I instead had written like a 0 here or a 1, it would not give me a strong signal. So it's able, this one little perceptron here is able to detect a 7. That's kind of that's what it's kind of tuned up to be or do. Okay, now what's important about the perceptron is that we have this convergence theorem. So we will, if we train it over like a whole bunch of like, okay, give it the output should be 0 when it's the number. Well, let's see if I can somehow erase this. I don't dare try that. Okay, so anyways, maybe I have to change the color. Ooh. So when the input is this right here, that's a 1. This output goes down to 0. Okay, so it only can just, and now if I take the 7 and I make a little bit different 7, so for instance, I do a 7 that looks kind of like this, something like that. Okay, it still goes off. It's kind of close, right? So it's kind of able to like do a little bit of a generalization there. But this is one single layer, so this is not deep neural networks at all. This is just one single little layer. Okay, but it's good to start here because this is like the building block for the what's the MLP, which is the multi-layer perceptron, which is basically the deep neural network if it goes, if it gets stacked. So how does this work? Okay, number one, the one thing that's missing here in this diagram here is that we have a W sub 0, which is always clamped to -1. So it's like this threshold thing. So it can reposition the actual function. So we actually have, in this case here, we would have 5 inputs. In this case, we have 1, 2, 3, 4, 16 inputs, and what happens then? 17 inputs because we have then a threshold as well. So and the threshold is always clamped to it's always clamped to an input of -1. Okay, so it's just going to be a repositioning thing. But the weight associated with the threshold weight is that's going to vary as we do the learning. Okay, so what do we have here? So we have what we do is we just do a linear, we just basically do a linear transformation here to calculate the sum. It's easy enough, right? But then we put it through a nonlinear function. In this case, we're going to put it through a sigmoid. Okay, so typically, or historically, it was the sigmoid function, which I'll define this in the next slide. So remember that, like, because of the nonlinearity, like, okay, if you think about it from linear algebra, if I'm going to like chain these in a big set of layers, like, and I'm just doing linear transformation, so I don't have any nonlinear activation function, then linear algebra tells that all collapses down to one single linear transformation. Okay, so the linearity is the nonlinearity is what's getting it so that it's not collapsible. All right. Okay, so let's see here then. So these are the common activation functions. Sigmoid is, okay, here it is. It's like, there it is. It's got the E and minus to the minus Z here, and Z is the input. That should be X, I think. But anyways, it gets put in here. And so if you just kind of do the math here, you'll see that what it does, it converges to 1 as X goes toward infinity or gets bigger, and then it'll go down to 0 otherwise. Okay? So it's kind of like this. It's called the squashing function also. So there's a sigmoid. Okay, then a more modern approach is this rectified linear unit. So this actually has better computational properties. And then we have something that will range between 1 and -1, which is the hyperbolic tangent. Okay, so these are just, and here are the definitions of these things. So you can, there's like max of 0 and X here. So when X goes to minus, it just turns it to 0. And then you might think here that we have, what do we do with origin there? So these are all nonlinear, right? Because they're not just linear relationships. And they're all differentiable if we just assume that the slope of the ReLU is at 0 is the slope of 1. Okay, just kind of like do that by definition. And then what's interesting is that all of these actually have found some backing in the literature that they have some biological plausibility. Okay. Right. Okay, so let's look at the sigmoid function here, and let's just kind of like let's do a little bit of math here, just so we can kind of try to get to know this in our bones about how this really works. So there's the sigmoid, 1 over 1 minus e to the x, right? And then it just, you have to just kind of take it on faith here that this is the derivative of the sigmoid. Okay, that's the first derivative of the sigmoid. And then what we have here is we have y is what, okay, so when we're gonna, so y is like, what is the correct answer? Okay, what is so x is the input. So x, notice here, x is a vector. So x could be like those 17 values. Now, in a particular arrangement of those 17 values, one of them forms a 7. So then the y in that case should be 1, because you say, well, this is a 7 here. Okay, so in that example, in that training example, that's a 1. If it's a 0, the whole thing's a big 0, then the y in that case is 0, right? Because it's supposed to be not a 7. Because this is a perceptron that learns the digit 7. Okay. So what we have here then is we have what's called the loss, or people used to call this like some variant of an error, but the modern terminology is to call this a loss. Okay, that is how lossy is the thing. Loss should be 0. If loss is 0, then it's doing the right calculation. But what the loss is basically is this is, okay, it should be 1. And this y hat is, well, what does the given settings of all of our x, the whole 17 x values, what does it actually give us when we put it through the actual function? Here's the function where we're just doing, it's just a transpose here of the weights times the x as the input. We do the kind of the linear combination there that way. Then we add in the threshold element here, or the threshold value. And then we put it through the sigmoid. And whatever value, let's say the value that comes out from that is like, okay, 0.86. So it thinks it's kind of a 7. This is kind of a strong signal for 7, but it's not perfect. It's got a loss of, well, in this case, we're using mean squared error as the loss, so you can calculate what the loss is, okay? So that's our loss. Now, we're going to calculate now the derivative, or the gradient, okay, with respect to the weights, okay? So we're doing, we're basically, how does the loss change when we wiggle a weight, right? That's kind of what it comes down. So it might say like, okay, this one particular weight here, what happens if I wiggle that weight, right? So that is dw sub j. So I go to this one particular weight and I say, how does the loss happen when I wiggle that weight, all right? And that's basically what we're doing, is we're calculating the derivative of the loss with respect to that weight. And then this is just some simple calculus of the chain rule. So you see the 2 here, taking the derivative, kind of pushes it all the way through. And then we get like the final, if you just kind of go through the math here, you'll see that it works out. And then what we get is we get basically that, well, okay, so this winds up being what the derivative is. And therefore, we take this learning rate, this alpha, and we just basically take the derivative with respect to the loss, and then we add that to whatever the weight is. So that's pushing the weight in the proper direction to minimize the loss, okay? So this is all there is to it. This is the math. And we'll see later that you'll get some code that does exactly this, so you can kind of know this in your bones, that this actually works, okay? So at this point, let's do this. And usually when I'm as you might imagine, I'm a firm believer in this kind of code as truth kind of ethos. So math is one thing, but let's go down. Let's nose it down into the code, and then we'll see what's going on there. Okay, so let's do that now. Okay, guys. Let's look at this code here. All right, so this is the perceptron peer code, which will be part of your recitation. So what I want to show here, these are some simple functions that we want to learn. Right, so this basically goes from the inputs are 0, 0, 0, and the output should be 0. That's for majority. So if you look at this, like, okay, if all of them are on, that's a majority. If basically 2 or more are turned on, then we get the majority function. One hot not is basically, it's just inverting the first one. So these ones are irrelevant, these 2 here. So basically 0 gets inverted to 1, 0 gets inverted to 1, etc. Okay. Now the XOR is kind of a generalization of exclusive OR. Basically it says only one of them can be on, and then it'll give you it'll be true. So if it's on that point, on that point, on that point, these are all ones. Otherwise, it's zero. So I forgot to kind of say this in the lecture, but this is not expressible. A perceptron, a single perceptron cannot express this function. And in fact, that's actually what kind of doomed the research, that and Rosenblatt's boating accident. That doomed the research through the 70s. So Minsky and Papert wrote a pretty scathing book about perceptrons where well, I'm not sure it was scathing. It was actually really well done. It was very detailed. But they show the inexpressibility of exclusive OR via a linear separability. If you want to look into that, so you'll confirm that you can't express exclusive OR in this code here. But anyways, the code. So this code is in pure Python. So this is not Torch. I just wanted to start out with something that was really kind of very simple. If you have some basic Python, you'll be able to understand what's going on here. Dot products, right? Okay, that's just doing a dot product. A ReLU. So these are the ReLU, the sigmoid, and the hyperbolic tangent. Those are all expressed here. And if you pass in the derivative being true, then it actually calculates the derivative. So in ReLU, if x is greater than 0, it'll return x. And it's not the derivative, then otherwise it'll return 1 for the derivative here. So it's again, here's the definition of the derivative of sigmoid right here. That's the derivative. So if the derivative is true, then this is what gets evaluated at x. Right. Okay. These generate random variables. This is uniform between 0 and 1. This is uniform between -1 and +1. This is just zeros. Okay. Forward and backward. Okay. So what this is doing is this is taking the example. Let's see here. Actually, let's see what this is actually doing. This is the train. So let's for instance say we're going to train the ReLU. Using ReLU as an activation function, we're going to train for majority, and then we're going to set weights basically from -1 to +1. Let's do that. Let's actually change this instead of that. Let's do uniform 0 to 1. Uniform 0, 1. So we're passing in the function, not the function call, right? Okay. 1,000 epochs, and then print the weights. We're not going to show the weights as we do it. So actually, let's just run this, and we'll see kind of how this goes. Okay. And I'm not even going to debug it. I'm just going to run it. So if we go up, if we scroll, oops, one sec here. A little resizing here. Oh, man. Just want to get a hold of the. Okay. So if you notice here, this right here is it's so this is for majority. So it's basically saying, oh, this is giving us back a value of this is false. So there's an error here. This should be 0. So it's giving back a value of 1.5 something when you put in 001, but it should be 0. So that's the size of the error. This is the size of the loss because it's in this case here what we're doing is we're doing mean squared error, and this is the gradient. So this is the actual way we should kind of affect, or the directions in which we should push the weights. So as you see here in the beginning, it's just random. So it's the average loss. It's just kind of throwing darts at the board in the very beginning. But as it goes through the whole thing, then it gets down to a very, it's pretty much capturing it. So what it's doing is it's saying, if you notice here, 011 is getting the value of 0.7. 224, etc. So if you use 0.5 as the separability criteria, then you would perfectly discriminate and you would perfectly have learned majority, right? Because what would 101 be? Well, that would be that's above 0.5. So then would say, yeah, majority are turned on. What if we have 100? Well, that's 0.1252. So that would be below, and then we would say no, it's not a majority turned on because there's only 1 of 3 turned on. Okay, so this right here, you can play around with this. And what you can do is you can see here that this is, everything's here. So if you really want to understand it, you can look here. So this right here is that simple calculus that I was talking about. So what it's doing here is it's going to return the gradient. So it's going to push it through, and then it's going to go and it's actually going to set the gradient here based on the slide that we have that just kind of did the derivative and the calculus. So you might want to go and verify that you understand this completely. So okay, so that's and then you can play around with different problems. And again, as I said before, once you try XOR, it's not going to work. It's going to be it's not going to be able to capture that. Okay, so let's look then. We want to do the same thing, but we want to use PyTorch. But before that, let me just show you this basic torch example here. So so you have to install torch in your environment, pip install torch or some such. That's going to be, it can be a little bit of a tricky thing. It depends. But once you have it installed, then you can run it. So let's just look at here and see what torch allows us to do. This right here is creating a tensor. So in machine learning, tensors it just means multidimensional, like beyond just a two-dimensional matrix. It's like an arbitrarily dimensioned or arbitrarily shaped matrix. So this is a 4x2 by 10. So it's like a block of a three-dimensional block, if you want, of numbers. We'll take a look at that in a second here. Then we have a simple vector here, and that vector then notice here we're doing the operation across the vector there, multiplying every element wise. These tend to do element wise operations. So not tend to, they do element wise operation. So it's going to multiply each element by 10. This is just giving us a zeros matrix. And then if we notice here, we can either do it one way or the other. We can do it as the torch.matrix mult, or we can use this operator that's been defined for torch. Right, let's breakpoint it there. And then we're just going to run through here. Okay, we'll take a look at what's going on. Right, okay. So if you notice here, right down here, there's the and I'm not sure I want to do that. No, in fact, I know I don't want to do that. It keeps it simple here. View as an array. View as an array. There we are. That's kind of interesting. So this is like this little A right here. And then if you think about it, okay, so X, so I guess the question to you guys might be like, well, what's the shape then of R? Let's see here. Well, we can look at R. R is the result. Actually, before the R, let's look at the at X here. So X, I don't know if I dare do that. Let's see. This is an array. Okay, well, it's got some. Yeah, it shows like that, and then you can go to this one here, and I guess you can go to here. Anyways, X should be. Here's X. Let's not even do that. Let's just view it as a. Just view it this way, right? Okay, so you can see it here. Here's the data. So it's 4x2 by, okay. All right. This seems to be something new. I'd really rather just view it raw, but okay. Anyways, you guys can play around with your own settings here. Not what I wanted to do. Okay, I'm going to pause this. Okay, I guess I'm back to it now. I'll have to edit this out, or maybe I won't. Anyway, okay, so now we're back. The key point here is just that it's just, I mean, all Torch is just a way to do, it's like, it started out as kind of a library that does this kind of like linear matrix multiplication, matrices. So there's a whole bunch of stuff inside of Torch, of course, other than that. And we'll kind of take a look and see something that's pretty cool about Torch here. So let's do this. Let's look at this. So this is another example of Torch that we're gonna just to kind of get warmed up on Torch here. So notice what I'm doing here. I'm basically saying, okay, the shape. So the shape is just an array of 3. Okay, and so what I'm doing here is we're going to have 3 items, and we're going to have the cost of each of those items, which is going to be random between essentially 0 and 1. And then we're going to have the amount procured per item. So this is how many of these items we're buying, okay? And that's going to be between 0 and 10 of these items that we're buying, quantity. then we're going to have so you can buy fractional amounts. Maybe this could be like some material where you can buy fractional amounts. All right. Then we have the price per item. So this is what we can charge customers per item. And then we have the demand per item. How many can we sell of these? Okay. And then we have the amount sold per item. And so this, so if we don't produce enough, then we just, if the demand is greater than what we produced, then we can only sell what we produced. That's what this is going to wind up being here. So it's doing a minimum here. Okay, so it's applying these operations here. So you can play around with this a little bit. And then what we do is we do this Hadamard product, which is the element wise by element wise. So basically, say the revenue per item, that would be the amount we sold times a piece in kind of element wise by the price. Okay, so you can kind of it is kind of pretty straightforward. And then we have the expense per item. That is basically how much we paid for it. Okay, now we have profit or loss or P&L statement per item. And that'll just be the revenue minus the expense on a piecewise basis. The net, of course, will be the sum over the profit and loss. Now, here's what's really cool about PyChart. We've gone through and we've defined a computational graph where we're pushing through these values. And then at the end, we're going to wind up getting a final result, which is our net profit and loss. When we say, now notice here on some of these, we say requires gradient. So this amount, so these are essentially the two things we can control. We can determine, well, how much of the amount are we going to buy of the items per item, and then what is the price that we're going to charge per item. Okay, and these are both saying they require a gradient. So these actually, so we've defined like this kind of like steps of computation, and then what Torch is going to do, it's going to push back and it's going to discover what's the gradient that would maximize our net profit. Okay, so this is actually kind of a useful thing to be able to run. So let's just run it and see what the output is, and then we'll see if this actually makes sense. Okay, so let's take a look here. Cost per item. Okay, so item 1 costs 0.5, 0.47, and 0.25. The amount we're buying of each of these is 5, 1, and 8.8. So these are all kind of randomized. Now the price that we can charge is 0.21. So item 1 is very bad because we're taking a loss on item 1. See that? So the cost that we're buying it for, but then the price we can charge is lower than the cost. So that's not a good thing to do. This right here, though, is better because now we're actually seeing that there's going to be a profit on that item. And likewise here. So the second and third items are actually good. Now here are the demands for them. And then the amount sold. So these are the amounts sold. So there's the demand. We can fill up the full demand for that. Since we didn't produce enough of item 2, we can only fill up the demand partially here. And then we fill up the full demand for the third one. Okay, this is the net profit and loss. So we're losing. All right. So then the question is that how should we bump stuff so that we can actually make a profit? So what direction? What's the direction we're going to do this in? And this is the kind of the gradient. So it pushed it back. So it did it forward and then it went back to the computational graph and pushed back the gradients. And this is not neural nets here. This is just an arbitrary computational problem. So it's showing kind of what Torch can do. So amount, the price gradient. Yeah. So here's the price. We should charge a lot more, obviously, for item 1. It's not so important for the other items. We should produce less of item 1. All right. So the example doesn't quite work because you can't just change your prices and then expect the demand to stay the same. But sometimes this elasticity of demand, right? Okay, right. So this is kind of a little thing to play with, but it shows you kind of what just in a very kind of for something completely different, it's showing us how these gradients, how Torch has this ability to form computational graphs and then push back the gradients. So it's a very general kind of capability inside of Torch. Okay, now let's look at Torch applied to the perception. Let's do the perceptron problem, but let's show it in Torch. Okay, so this is here. What we have is some interesting stuff going on here. Okay, so notice right here what we have. If CUDA Okay, so what's the device we're going to use? And then this is kind of some nice coding here, which says basically, well, if we can put it on CUDA, so if we have GPUs, let's park this. Let's say that the device is going to be CUDA, and then the inputs are right here, and then we put those on the device. So what this is doing, this is going to push it over onto the GPU, if it's if that's available. So majority, XOR, and one hot not, these are just defined right here. Right, so these line up. These are basically, these are the inputs and these are what the outputs should be. So there's kind of a little bit of like trickery there to kind of get what the outputs are, given the space here of the inputs. Okay, so in other words, 0, 0, 0 under majority will give us a 0. 0, 0, 1 will give us a 0, right? Okay, so you see it. XOR is defined there, and one hot not. Then we have this class of the perceptron, and the perceptron takes in the input size, and the input size is what that's going to be, what, 3, right? Let's see here. What is my input size here? Where do we instantiate this? Yeah, input size is 3. Okay, and then what it does is it'll also take in the activation function, and it will set this thing up. It'll set up the whole. It'll set up right here is just setting up. It's kind of initializing its layer, the activation function, the layer, and initializing this NN module. And on the forward part here, what it's doing is it's just calculating what the output should be. So it's using the activation function. So first it's it's just determining what the output is based from X, and then through layer one. So it's doing the kind of linear transformation, and then it's taking the output from linear transformation, putting it through the nonlinear activation function, and then return it out. Right. Okay. So this right here, we have ReLU. Maybe let's do it as a sigmod. So we'll just kind of run this thing. We're going to run this as a sigmod here, and then when we do this as a sigmod, and then we're gonna, which one are we going to learn? We're going to learn. All right. So it's what it's doing here. The model is a perceptron there. Okay. So it's putting it to the device again. So it's going to CUDA, and then the criteria here then is mean squared error. And then number of epochs is 100. Learning rate is 0.01. Optimizers. This is the actual optimizer called Atom that's within Torch. And then we'll just do the non-batch. There's 2 aspects here that you might want to study, but basically non-batch learning of the majority function. So let's just run this puppy, and then we'll see that this will actually get learned. Okay, so what is the majority here? So this is the final. Okay, so this is the final result that's coming out. So with 0, 0, 0, yeah, it's essentially doing the same thing. So 1, 0, 1, it's going to give us something. So if we took 0.5 as how we're going to linearly separate that's the kind of the threshold that says if it's over that, then it's a majority. If it's under that, then it's not a majority. That would then discriminate this. So as you can see, it's converged here. And if we go back to the very beginning, you'll see that, well, I guess you won't see. Well, there was a loss here. So the loss kind of bounced around here, but what did the loss converge to? Yeah, so loss got pretty low here. Okay, right. Okay, so that's this is enough. I mean, you guys are going to get the ability to kind of play with this, and yeah. So that was the code. That was us nosing into the code. Those computational graphs, and then we saw this whole thing kind of run through Torch. So now these are real simple, like little examples here for just the single layer perceptron. Now, what happens is that what we really look at here is we look at deep learning. So we're looking at multi-layer perceptrons. We're going to stack these things out. So when we do that, we bring up what historically has been called a hidden layer, so what we'll see here is we see that there's a lot of times you'll just have like a single hidden layer. But what the insight is behind deep neural networks is that you can really kind of like stretch these things out, and you can kind of arbitrarily build like different computational graphs for your particular problem. So that was a great insight. Okay, so later on, I think we'll flash it next time. We'll flash, or not next, not next lecture, but the lecture after that. I want to flash up just to show you what the the backpropagation algorithm is pretty hairy, but I want to show it at least kind of like so we can look at the thing and try to get some sense of it or feel for it. It's pretty hairy though, but we'll do that later. So there's one last thing I want to talk about just quickly here, and that has to do with, if you recall. We had this issue here back with grandmother, where I was saying, oh, well, if grandmother is the majority here, if grandmother is got like, let's say that we push through this image and that the grandmother cell here is like saying, oh, it's I'm activated now here with a 0.98 or something, and then this other one over here for the grandfather says, oh, I'm activated with a 0.45, okay, and this other one over here says, as a Buick says, I'm activated with a 0.16 or something less. So grandmother is got the highest value, no doubt. And by the way, a lot of times the values that come out of these, they're not like stopping at 1. They accumulate, so they can be like 4.5 for this one here, 3.1 for this one here, and 1.2 for this one here. Okay, so that can be what the actual output is, or the actual activation is at that part of the network. Okay, so what's the problem with that? The problem is with that is that they're not normalized in any way or any kind of coherent way. So what softmax does is what softmax will do. See, this is again the whole. So let's just look at an example. So let's say that thing about like determining the outputs we got out of the thing was 2.3 for grandma, 1 for grandpa, -3 for the Buick, and 0 for the telephone pole or something, right? So you might say, oh, it must be grandma because she's the max. She's like the maximum value. But what's better to do is to do a normalization where you kind of like take all these values and you divide by all those values in this particular softmax formulation here. So you take them to the exponential to calculate a softmax. And when you do that, you get out a probability distribution. So then you get out, oh, it's a 0.72%. 0.72 is the probability that is grandma, 0.198 that is grandpa, the Buick, the telephone pole. Okay, so this is something that we push through, and this has a lot of nice mathematical properties. So we'll see here, especially when we talk later about cross entropy, that this is the way you want to do it. You want to push things through a softmax at the end, because that's kind of a technical detail, right? Okay, so let's finally then talk about our first. We're going to look at a multi-level perceptron doing this MNIST, which is a very famous example where we're trying to actually learn to classify digits. Okay, so this is a nice data. This is a nice data sample that you'll actually work with in recitation. And then let's and then we're gonna let's nose down into this code so we can see this at work, a PyTorch at work over a MLP, a multi-layer perceptron. Okay. So that was your kind of your quick. This is okay. So yeah. So this was your quick kind of crash course in deep learning and in PyTorch, and this will be useful in RecitationOne, and the initial version or initial release of RecitationOne, not the full release, but the initial release is coming out today. So then you can take a look at that if you want to get a jump on this. Okay, thanks. Okay, so now let's show this quickly. Let's show kind of a bit more advanced example of the MNIST example. So the MNIST example, here's the code. So what we have here is here, let's just run the whole thing so that we can see kind of what it does. Run MNIST, okay? And then when we run it, what we get out here is that looks like that's here's some examples. A 0, okay. The first example, that's a 7. See, does that kind of look like a 7? This is just printing out the data example. This right here is a 2. Yeah, it looks like a 2. This is a 1. Okay, so these are like 28 by 28 bitmaps, although they're actually real valued if you look at the actual data here. And now it's running here. So it's kind of, what it's doing is it's trying to it's going through these examples. This is like the first, it's plucking out. Okay, there we are. Yeah, so we got, we just did the full training, and then now we have, when we do it, we test it, we get 97.04 accuracy. So that's good. So let's look and see what the code is doing here. I'll just do this very quickly because, again, you'll play around with this. But this right here is going to act. This is actually going out and using some of this stuff, these data loaders. So it's actually able to go in, and there's a lot of data. There's so much data out there you can play with. But in this case, it's the MNIST data. So, right, this is actually just printing out those examples that are just kind of plucked. If the value is, if the grayscale value is above 0.5, then it puts an asterisk. That's where you saw the 1 and the 7 and the 2. Here's the neural net, though. But notice what we have here now is we have multiple layers here. We have a hidden layer. So we have layer the first layer, that's a hidden layer. And then we have that going through a ReLU, and then it comes out to another. And then we have a final layer here that's doing another linear transformation. And then what we'll see here is actually it's going to be doing this maximum entropy, which I'll discuss later. I'll discuss in the next lecture. Yeah, so you can kind of like just kind of go through this, and you can see kind of how it's working. So it's very little code here. So it's easy to kind of study and to see. So, right. So yeah. So I will release recitation number 1, the initial part of recitation 1, so you guys can get access to this code and you can start playing around and get your environment set up. Okay, great.